represents the oxidation of copper, where copper is going from copper atoms to copper ions. Now remember that oxidation is the loss of electrons, which will mean the oxidation number has to increase. So copper atoms have the symbol Cu. If you forget, double check on table S. And copper ions also have the symbol Cu. Now the difference is atoms are electronically neutral because they have the same number of protons and electrons. So the oxidation state of all atoms in their natural state is 0. Wow, the oxidation state of copper here is going to be 2. They tell us it right here in the reading passage. So we have to write the balanced half reaction. So we have the copper atoms becoming copper ions. Now, the atoms here are balanced because I have 1 copper on each side of my reaction, but the charge isn't balanced because 0 does not equal positive 2. So we're going to have to add in electrons. Again, you always add the electrons to the more positive side. So we're going to add the number of electrons you add is always the difference between your 2 oxidation states. In that case, it's going to be 2 electrons. So this is the balanced half reaction, and we make sure we did it right because this is oxidation where my oxidation number is increasing and I'm losing the electrons, and all species lost in a chemical reaction are always on the product side. Now the next question is referring to reference table J. So before we get any further, let's pull that reference table up again. Here we're asked to explain using reference table J why when iron is placed in contact with copper, it is oxidized. So on reference table J, I see that iron is located above copper on reference table J. Remember, reference table J lists activity, and both iron and copper are metals. They want to lose their electrons to obtain stable, noble gas electron configurations. We can see here that iron is a better loser of electrons than copper. So what we can say is that iron is more active than copper. Therefore, iron is going to lose their electrons and copper is going to gain electrons. In the next question, we're asked to write the reduction half reaction for the equation provided. So we can remember that reduction is a gain of electrons. And it's called reduction because our oxidation number will go down. The first thing we'll want to do is assign the oxidation numbers for all the elements in the reaction. Now here we'll again see that we have nitrate. It's in parentheses, which is a good clue that it's a polyatomic ion. On reference table E, we find that nitrate has a charge of -1. We see nitrate over here on the reactant side also. We'll place it in parentheses and give it a charge of -1. Now going on, let's look at the charge of the rest of the atoms. On the reactant side, copper is solid and by itself. It's in its natural state. It's a lone element, so it has the oxidation state of 0. Now let's see if we can refer to our reference table to find the oxidation state of silver. Here we see silver can only have one possible oxidation state, +1. That makes perfect sense because the sum of the oxidation states of the ions in an ionic compound have to be 0 so that we assure that the number of electrons gained equals the number of electrons lost, and the reason the ions bonded together is so that they can both obtain stable, noble gas electron configuration. Now, when we look at copper on the product side, we see that it's in the compound copper nitrate. Now when I look up at my reference table, copper could have a charge of +1 or +2, so we're going to need to calculate it. I'm going to assign copper the oxidation state of X. Now when we look at the compound, we see that there's 1 copper and there are 2 nitrates noted by this subscript 2 here. So what we're going to do is we're going to circle these values and multiply them and find the sum. So that means 1 times X plus -1 times 2 has to equal 0. So here, copper is going to have the oxidation state of +2. And finally, we have silver. Silver's a solid, and it's all by itself. It's a lone element, so it has an oxidation state of 0. Again, to refresh our memory, we're looking for reduction. So the copper's oxidation state went from 0 to +2. That's not being reduced. That's being oxidized. But silver is going from +1 to 0. That is a reduction, so we're going to have to write the half reaction for the reduction of silver. Recall, when we write half reactions, what we're going to do is we're going to write the element that we're referring to separated by an arrow. Remember that, again, it's silver undergoing reduction. So we write silver separated by an arrow, and then we fill in the oxidation numbers from the reaction. It goes from +1 to 0. Its oxidation number was reduced. And then we're going to have to add in electrons. To determine the number of electrons, you take the difference in the oxidation number. The difference between 1 and 0 is 1. So we're going to add in 1 electron. The electron goes to the more positive side. We check our work to make sure this is mathematically correct. -1 plus +1 equals 0. So our half reaction is balanced. The last question asks us to balance the redox equation to the simplest whole number ratio. This can be done two ways. The simplest way here is going to be to simply balance the equation, though just the same way you've always done. A lot of people like to create a t-chart when they balance an equation. So when we create the t-chart, what we're going to do is we're going to take an inventory of the elements. Now, the t-chart is separated by the arrow, or the reactants and the products. So here, the atoms we have present are copper, silver, and nitrate. I'm going to keep nitrate together because it's a polyatomic ion and it's unchanged on both sides of the reaction. It just makes balancing a little easier. So when I look on my reactant side, I have 1 copper, 1 silver, and 1 nitrate. And when I look on my product side, I have 1 copper, 2 nitrates, and 1 silver. So I notice that my nitrates are unbalanced. To balance my nitrates, I can only add coefficients. Never add subscripts when balancing a chemical reaction. So I'll add the coefficient 2 here. Now, adding the 2 there means I have 2 silver nitrates. So in addition to now having 2 nitrates, I'm also going to have 2 silvers. So my silvers are not balanced. So what I'm going to do is I'm simply going to add the coefficient of 2 in front of the silver on the product side. Now, when I look at my t-chart, I have the same number of atoms on both sides of my chemical equation. So my equation is balanced. There is an additional way to balance this redox reaction. In order to balance the redox reaction, we can write 2 half reactions. In this case, we have the copper undergoing oxidation, becoming copper ions. So in order to balance the oxidation half reaction, what we'll have to do is we'll have to add in 2 electrons to the product side. Now, we already wrote the half reaction for the reduction of silver. Let's write that down one more time. Notice 2 things. The first thing you should notice is that I made special attention to line up my arrows. This is going to make my math easier later. The second thing that you'll notice is that the nitrate, whose oxidation number did not change through the reaction, is left out and not considered in my 2 half reactions. So in order to balance this, what we need to do is make sure that the number of electrons gained equals the number of electrons lost. In this case, that's not happening because 1 does not equal 2. So in order to do that, we have to multiply both equations by the least common multiple. The least common multiple between 1 and 2 is indeed 2. So that means that we're going to multiply this top reaction by 1, and we're going to multiply everything in the bottom reaction by 2. Now, since multiplying by 1 is not really changing the identity, we're just going to keep everything the same in the top reaction, and we're going to carry a 2 through everything in the bottom reaction. So in this case, the final step we'll need to do is we'll need to go and add these 2 reactions together. Notice that the 2 electrons on the reactant side will be removed because there's also 2 electrons on the product side. So that means that we have copper with a coefficient of 1. We don't typically write 1s in chemistry. And silver with a coefficient of 2. So notice this is 1, 2. And then on the product side, again, we have copper with a coefficient of 1, which we don't write, and silver with a coefficient of 2.